Hello everyone and welcome to We Meet at Digital Days. My name is Marie-Therese Kohl and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is the impact of contact resistance and plating on the performance of a connector. Our speaker is Dominik Zeller. He will hold the presentation and will answer your questions. But before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentation. Nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. You will find the chat function in the control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email afterwards. And if you still have any other questions left, just mail us at exhibition@we-online.com. We will try to answer all questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our event. You will also receive the link to the presentation in the next few days, and the recording will be available at our website shortly. But now I will hand over to our speaker, Dominik, and I wish you an exciting presentation.
Superb. I hope you all hear me and I hope you all see me. Yeah, thank you for the introduction. I'm going to go away with the folder. So here. Okay. Yeah, as already spoken about, I'm going to talk about the impact of contact resistance and plating regarding the performance of a connector. So the first is going to be, of course, the contact resistance. What is it? Then we will speak about contact zone parameters, eiSos, and different platings. And as a last point, I'm going to speak about mixing different plated connectors and if that's a good idea or not. Well, of course, it's always hardly depending on what connector you are currently using and using it for. I mean, contact resistance has many roles, and in this case, we are going to look regarding power connectors. Well, for power connectors, it's quite easy. The most interesting part is going to be to have a small contact resistance, because a high contact resistance is going to create a high temperature increase in your connector, and worst case, your connector is going to fail. By doubling the contact resistance, you also will double the temperature. And I mean, if you have an ambient temperature of 60 degrees and you have a temperature rise of 60 Kelvin, you are at about 120 degrees, and that's not a good spot for a connector. Therefore, regarding power connectors, a low contact resistance is ideal. Again, increasing the power, increasing the contact resistance will also increase the power losses. Yeah, next thing is going to be for data connectors. Here, contact resistance has a different role. Contact resistance is going to create a voltage drop, and this can be a bad thing depending on the voltage drop. The higher this voltage drop is going to be, the more likely it's going to be that your transmission is going to fail. So again, something you want to avoid. Here just a few examples. In the datasheet, we mentioned a lot of parameters, but in this case, contact resistance and durability or mating cycles. The contact resistance we state here is 10 milliohm max. This means the contact resistance is not allowed to be higher than 10 milliohm, the complete life cycle of the connector. So at 25 mating cycles, it still has to be below or max 10 milliohm. A small spoiler, we are way above, way below this value. Again, of course, if we state something in our datasheet, we have to test it. There are different tests, and some tests have a direct impact on the contact resistance, like the salt spray test. We salt spray test our connector plating for 48 hours plus minus 4 hours, and then we measure the contact resistance. And it's not allowed to, or it has to be less than twice of the initial value. If it's not, it's failing the test. Again, the same thing for humidity and temperature cycling. All of those tests are going to impact our contact resistance. How are we, Würth Elektronik, testing the contact resistance? Well, we are using the standard EAA 36423 low-level contact resistance measurement, so the 4-wire method. We are measuring the current and the voltage, and with both values, we are calculating the contact resistance. Yeah, well, if you look into the connector or the complete setup of the connector, you mostly have a female and a male part connecting each other. Then you have a solder point, in this case it's here, and maybe a wire. And all of those things will have a big impact on your contact resistance. However, due to time limitations, I will only speak about a small portion of this. If you are interested in the complete presentation, this takes about 1 hour and a half, please contact your sales representative at Würth Elektronik or maybe your field application engineer, because we are always willing to do an in-house seminar about this topic. Well, as I already told you, the wire will have a big impact. Also, the crimping resistance will have an impact. Then the raw terminal of the connector, the contact zone resistance, this is the part I'm going to talk about today. And of course, the next raw terminal material, and then the resistance of the solder. And all of those are together the contact resistance, and ideally as low as possible. Yeah, when we speak about contact resistance, we also have to speak about contact zone parameters, or eiSos, and of course the plating. We will start with eiSos. eiSos, here I have an example, a ZIF connector, so zero insertion force connector, typically used in combination with an FFC cable. We did a microsection of the mated setup. So here you can see the ZIF connector and the FFC cable. And only at this point, both parts are actually mating. And this looks quite big, but if you use a microscope, you will see that only a small area is actually touched by the connector itself. And where the connector is touching, those points are eiSos. So those spots are the only path the current is able to travel. So the more eiSos you have, the lower the contact resistance is going to be. Here, another example, a female part and a male part. Again, looks quite big, but it's not, because every plating we are using and everyone else is using is not a flat surface, but a rough terrain, like the Alps. You have canyons and you have peaks, and only where those peaks are actually meeting, their current is able to flow. And those spots are called diode spots. You also have a film resistance. Most of the plating is going to create an oxide layer to protect itself from oxidization. And this layer is going to be sort of non-conductive. Means either with a high current up or above 50 milliamps or a high pressure, you will be able to penetrate this oxide layer. That's also the reason why we are using plating. But that's another topic. And depending on the pressure you are going to use on the female part and the male part, the A spots are going to become more and more and more. Of course, the more pressure you are going to use, the less mating cycles you will be able to reach, because you have abrasion and metal relaxation and a lot of other bad things, and they all will reduce the plating thickness by mating and over time. And ideally, you will find a sweet spot. When you have no pressure, you have a lot of contact resistance, you have film resistance. With applying a bit of pressure, you will have film resistance and A spots. And at a certain point, ideally, you have a lot of A spots. And this is also typically the contact zone or the optimized contact zone of your connector. You always will have a small security margin because, well, as I already told you, metal relaxation is part of the thing. Also, tolerances can be a thing. And to be 100% sure that you will not fail your test, you will try to have a sort of security margin. Yeah. And I already told you, we are also using plating. Well, there's an easy explanation for that. If you look into metal conductivity, you will find that silver has or is the ideal conductor. So it has 100%. Copper is a bit less. So why would someone use gold or tin as a plating when the conductiveness of copper is so high? Well, copper has the good or the bad thing that it's creating an oxide layer on the top surface. And this layer, as you can also see in the diagram, is nearly non-conductive. I mean, it's a so low percent value that you will have to use plating in order to optimize not only the conductiveness, but also the oxidization safeness. The copper oxide is also a really good insulator for electricity, something you don't want, because then you will have a high contact resistance, high heating in your connector. So the possibility that the connector is going to burn is quite high. But the oxidation is, or the oxide level is also a protection against the oxidation, and therefore also a bit good. I mean, everyone knows the Statue of Liberty, and it's green because of the oxide layer. And because of the oxide layer, it's still standing. Yeah, and therefore we are using either tin or gold as a plating to improve the conductiveness and also to improve the overall mating cycles of your connector. The first metal you can use as a plating would be tin. Tin is quite good because it's cheap and quite good to use as a plating. As you can see here, I'm going to try to shift my screen a bit so I can see it a bit better. Again, we have copper or brass. Most of the time we have some sort of brass or phosphor bronze as the main contact, and then the soft tin plating. The tin plating itself is about 2 to 4 micrometer thick and will protect the underlying copper from oxidization. Also, it will improve the conductiveness. However, tin is also creating this tin oxide to protect itself from oxidization. And this is not very thick, about 0.1 micrometer thick, but it has to be broken so that current is actually able to flow. And this, as I already told you, can be done by either having high contact normal forces, so both parts are going to be pressed against each other quite hard, or by a lot of current. Yeah. However, this will have quite a good performance up to, I don't know, 50 mating cycles, but everything above has to be further increased or further improved. And how can we create a sliding contact and increase the mating cycles even more? Well, one answer would be just make the plating thicker. However, this alone will not increase the mating cycles by a lot. So what can we do? Well, the easiest way is to add underlaying plating. In this case, we are using nickel. So we have our copper or brass main connector. Then we have a hard nickel plating, 1 to 3 micrometer thick, and then we have the soft tin on top. This will create a sliding effect. So tin is going to slide over the hard nickel and will further improve the mating cycles by a lot, up to 100, maybe 200 mating cycles. But you will never use tin as a, I don't know, a communication connector. You will never find a USB-C connector with tin plating. It's not made for that. But if you look regarding contact zone resistance, in the datasheet, we tell you it's 10 milliohm max. And here you can see what the actual contact zone resistance is. It's 0.8 milliohm. So it's a lot smaller than we are stating in our datasheet. Of course, we have additional resistance like the raw terminals on both sides with 1.6 to 1 ohm. And we also have the crimping resistance 0.2 ohm, and the wire. In this case, it would be RVG 16 5 centimeter long cable. This has a typical resistance of 0.7, and we have the solder resistance. But even if we add everything together, we are way below the 10 milliohm. So as a conclusion for tin plated surfaces, the contact zone is only 25% of the full contact resistance. So it's not that big of a deal, but it's still a big deal. The security margin, at least at Würth Elektronik, is well huge, and as I already told you, the typical values are 0.8 milliohms. So it's quite low. Regarding mating cycles, there are different ways how you can test mating cycles. The easiest way is, of course, using a machine. The good thing with a machine is you have a defined force and you have a defined path the machine is able to travel, and therefore you have the ideal mating cycle. The ideal mating cycle is not often reached in the real world. I mean, everybody knows if you use a USB connector, there is 100% chance that you will stick it in the wrong way. And then you turn it, stick it in, and it's still not going in. And then you turn it back again, and then finally it's going in. Those are all mating cycles. If you are not able to switch in the connector, you always use a lot of force, or most of the times, a lot of people are using a lot of force. This is also not good. It will reduce mating cycles, and therefore we are using a machine. Yeah, what's going to happen if you use too much mating cycles? Well, that's quite easy. Depending on the stack of your plating layer, you will reduce the tin layer, and if the connector has a nickel underplating, it will also reduce the nickel plating, and copper is going to meet each other, which is theoretically not a problem because copper is a good conductor. However, as soon as you introduce humidity and maybe salt into your system, you will have a lot of bad time. Mini modules, we state in our catalog, we state in our data sheet 25 mating cycles, and we tried how long could we mate both connectors and then fail the contact resistance test. And at above 250, the test was failing. So there is a huge security margin on contact resistance regarding our connectors. However, there's a reason for that, because if we are failing the contact resistance test regarding mating cycles, there will not be a lot of plating left on the contact. And this is going to be looking like this. I mean, again, in the datasheet, 25 mating cycles. Here, in this case, we did 1000 mating cycles. What you can see is we lost a lot of geometry on the contact itself, which is not good. We also lost most of the plating. I mean, you can see copper, you can see part of it, a part of the nickel plating, and of course you can see the tin plating. And also the aberration was so high that it also affected the insulator, which is also not a good thing. Therefore, of course, don't use this connector with 1000 mating cycles. That's going to be insane. As I already told you, mating cycles will have an impact on contact resistance. Contact resistance will have an impact on temperature. And when you look into the diagram, well, it's not that critical. I mean, from 20 something to at about 40 Kelvin, yes, that's true. But this test was directly after the mating cycle test. When you leave this connector alone for, let's say, 3 weeks and do the test again, you will see a big impact. You will now see two pictures. The first picture is a complete new connector out of stock, and the connector that was mated 5,000 times or 1,000 times, and yeah. And the difference is easily seen by the temperature difference. This one is directly out of stock, and this one is already at 125 degrees Celsius, which is a lot, and most of the time too much for the connector. I think this connector should be about 105, the max temperature. And yeah, we are way above that, and that's not a good thing. So what is the easiest way to increase corrosion resistance, remove wetting corrosion, and decrease the contact zone resistance? Well, the easiest way is use another plating and choose the plating regarding its likeliness to oxidation. This means, well, the easiest choosing would be choose gold because it's resistant to corrosion. We have some plating that has a passivating effect, like silver or tin. Passivating means it's going to form a tarnish when we speak about silver, or an oxide or some sort of oxide layer on tin. And you can also see iron is sensitive to corrosion. This means when iron is going to corrode, it will not stop on the surface, but it's going to go into your material until nothing is left anymore. Therefore, iron is not going to be the ideal plating for the connector. In this case, well, it's quite easy. We are going to use gold. Gold, however, has some negative effects also. The most easy visible would be, well, the price is going to increase. Therefore, we are reducing the thickness of the plating. Most of the times you only need flash gold. Flash gold is about 0.01 to 0.02 micrometer thick. Again, the soft tin was 4 micrometers thick. This is way, way less. And of course, we are also introducing a hard nickel underplating. Not only regarding the sliding effect, but also, and that's the most important part, regarding the protection. What protection? Well, if we would not use nickel as a protection layer, gold would diffuse into copper or brass. In brass, it's even worse, and would create non-conductive areas. So not only would it not protect the copper, but it would harm it regarding the contact resistance. So hard nickel is a must in this case. Well, and then you automatically increase the mating cycles by a lot, 1,000 or 5,000, depending on the shape of your contact. We did global measurements regarding our gold contacts, and well, as you can see already, gold contact is typically about 0.5 milliohm. Again, the contact zone is mainly ignorable when we look regarding contact zone and small cable, because the smaller your cable is going to be, the higher the contact resistance is going to be introduced into your system. Again, we have a lot of security margin, and what I often find quite interesting, gold and tin, if you compare both of them, their values are not that much different, because I often hear, well, I'm using gold-plated connectors because of the contact resistance. Yes and no. As you can see, the difference is not that big. Yes, of course, if you have something, or if you need a contact that's stable over a very long time, and also stable regarding humidity and salt. Of course, you are going to choose gold. So as an easy example would be the airbag. An airbag is highly likely or hopefully a gold contact. But for a lot of connectors, tin is completely fine. Again, a mating cycle over or slightly over the datasheet values. In this case, we had the pin header. In the datasheet, we have 50 mating cycles, and we did it up to 700 mating cycles. The same thing happens as with tin-plated connectors. You will lose a lot of your surface plating, of your surface protection, and overall, over time, it's not a good idea to go up this high. But only regarding the contact resistance, it's quite stable until 700 mating cycles. How can we now further increase the number of mating cycles? Well, we can do two things. We can use nickel palladium, and the nickel palladium is getting a gold treatment of 0.05 micrometers. So it's going to be thicker. But this alone is not going to change the mating cycles by a lot. You will also have to change the overall geometry of your contact zone or of your contact. By making it bigger or wider, you will reduce the aberration on one part, and you can spread it out a bit. And with this, you are able to reach 10,000 mating cycles. Again, in the datasheet, we are mentioning 10,000, but we did a test, and up to 30,000, you will have a quite stable contact resistance. But again, if you leave it for 3 weeks, it's not going to be this low anymore. But you can also see a fun thing. The highest peak of contact resistance is at about 40,000 mating cycles, and then it's going down again. There is an easy explanation for that. At this point, nickel and nickel is touching. Both of them are not ideal conductors and have a high contact resistance. And after both layers of nickel are slightly vanishing, the contact resistance is going down again. Yeah, but of course, if you are 20,000 mating cycles above the thing we are specifying in the datasheet, your overall connector is going to be quite severely damaged. Not only will you reduce the plating down to maybe copper, but you will also, well, the plastic is going to be eradicated. And yeah, that's not a good thing. So better not do that. Now, how to plug and or unplug under load? Gold has a small negative effect regarding arcing and high current. It tends to material migrate, meaning it will transport from one contact to each other, or due to arcing, you will, well, basically break or burn off the plating. Therefore, ideally for this case, you would use another plating. We have now two parts, the switch contact on the left and on the right side. And on the left side, you typically have the gold plated switches for low voltage, low current applications. And on the right side, they are mainly silver plated. Therefore, they are often able to withstand 250 volt and 60 amps. And also you can see regarding electrical life, 20,000 to 1 million. When we speak about electric life or a switch cycle, we always speak about the full cycle. That's really important. So if you use a takt switch, the pressing and releasing of your finger and releasing of the contact is one full cycle. I talked about arcing, and that's a thing that's often common when you have current and voltage applied to your connector or to your takt switch. By releasing both contacts and going to touch together again, there's a high chance that an arc is going to happen, a small one, and it's of course not burning a hole like this, but it still will damage the plating over time. Again, when you press them together, you will have an arc. And you can now either use silver. Silver is going to be vaporized over the cycling times you will define in your datasheet, or you will create specific shapes. Like with modular checks, there are sometimes modular checks that are able to be plugged and unplugged under voltage. Then they often have a contact zone and let's say a touching zone. So the touching zone is where the arc is going to happen, but that's not the actual contact zone. And therefore it's not going to be, or it will not have an impact on the performance of your connector. Why is it so important that we speak about plating and A-spots and plated connectors? Well, sometimes it can happen that different plated connectors are in use. And this will create a quite negative thing I'm going to present now. The first thing is we always talked about oxidization, but what we not spoke yet about was galvanic corrosion. Depending on the metal, the two metals you are mating, you will create a voltage drop. Every metal has a specific anodic voltage. In this case, gold has 0.13. And if you made gold and gold, the voltage drop is going to be 0. So you are in the green line. In the green line, there will be no galvanic corrosion. If you have a gold contact on the one side and let's say a silver contact, there is a chance that either metal A or B is going to attack the other metal. This is highly depending on the humidity and also on the temperature. Those two are going to increase this phenomenon. Also the size of both metals have a big major impact on that. And the differences in materials, meaning if I have now a gold plated contact and a brass, we have a voltage of 0.52. This means, in this case, metal A is going to be attacked, or gold is going to attack the brass. And this is also going to happen with tin. You are in the safe zone when you are approximately a bit below 0.3 volt. If you want to be on the safe side, ideally it should be even lower, 0.2 volt or 0.1 volt. And if you ignore that, mean things can happen. In this case, a concrete example would be we have a gold-plated connector and a tin-plated connector. Both have a voltage difference of 0.67 volt, and galvanic corrosion is going to be a problem. And what did we do? Well, we used a gold-plated SIF connector, so this one, and a tin-plated FFC cable. And we applied salt spray, and after 144 hours, you can clearly see on the right side that gold attacked tin, and tin is gone completely, and you can see the bare copper. It's not 144 hours. At about 72 hours, you already can see the plating vanishing. And that's a problem because in this area, the connector is also connecting to the FFC cable. And if we have now high humidity or again, the salt spray, my copper is going to, well, oxidize. And this is going to be a big reason for my failing transmission line or my failing transmitting the data. Therefore, ideally, never ever mate different materials, especially if it's a gold and tin contact and small pitches. A small thing I forgot when I spoke about tin. When we have a tin plating, we often use the nickel underplating also as a barrier for whiskers. Whiskers as the hair of the cat will grow on the surface of tin, small tiny hairs, and those can short circuit small pitch connectors. That's another thing I just wanted to mention. Well, and then we are at the end of my presentation, and now you are able to answer questions, and
Yes.
I will.
Thanks a lot, Dominic. Due to the time, unfortunately, we won't have the time to answer the questions right now, but we will answer them for sure right after the session via email, and you can also send us your questions via email if you have some. But for now, I would say thank you very much for your attention, and I hope you enjoyed our presentation. The next presentation topic is Require Sonnenwagen Tech Talk with Team Sonnenwagen Aachen. Thanks a lot and goodbye.
Thank you.